Hi, it's David from Electric Teaching, and I'd like to do part 2 of calculating a volume using integration. In this case, we're going to take the same area that we did before, where we rotated it around the y-axis and created a solid kind of acorn-looking shape. We used a disk method since it was solid. It was filled with solid areas. So then we used a disk method, and because we went around the y-axis, and I showed you why there was a dy involved, that forces us to use dy and disk. Remember, this is always the question. dx, dy, disk, or washer. Again, a shell method is also out there, which we'll cover in another video. So in this case, I'd like to mix it up by rotating it around the x-axis. So we are going to rotate it around the x-axis instead of the y-axis this time. So if I do this rotation around the x-axis, the first thing I always tell my students is to draw the reflection to get a visual here. So I'm going to try to, as best I can on this digital pad, to try to draw the reflection of this area in this case, and I've got it then filled in. I would fill this in, but I'm not going to fill it in because I want to try to draw all the circles that are involved after we rotate the area. So if you rotate the area 180 degrees, it would look like this in a quick little snapshot. You rotate it all the way back around and fill that area in, you will get a cylinder looking shape. In fact, the outside of it would be a cylinder pretty much exactly. This is going to be kind of hard to draw circles on this shape, and I'm going to do on this digital pad, but I'm going to do the best I can here. So what we have is we have the idea of a circle on the outside. A circle on the outside, so I'm going to pretend I'm looking in this way with my little 3D model. So if I was to turn this flat object into a 3D model, I'm going to be viewing it this way, so I would see the entire elliptical edge from this perspective, from this angled perspective. If I was looking straight at it, it would be a perfect circle on top, but it would be hollow. You can see the inside of this would be hollow, and there would be, if I looked all the way through, I would see the circle down here. Now, because I'm looking at an edge, I'm going to draw this with a dashed invisible side over there. I think a lot of what we're trying to teach in calculus is more of art-based as well as the algebra-based to get you able to draw these objects in case you enter an artistic world like engineering, architecture, or many other things out there. So there's a lot of good, healthy art practice, I believe, in this. So the outside shape, if I was to continue drawing like another outside, let me see if I can draw one way over here. So the bottom of it would also, I don't like that one, let me try it again. The bottom of it would continue with this cylindrical shape, where I would see then the outside edge and then this disappearing off. I don't want to draw all of it, but you can see I would have then the back edge of this circle deep inside there. So you can see the full outside is a solid cylinder. If I was to look at a cross section from this view, all I would see is like this can, this flat can that's fallen over. From this view, I would notice that it's hollow, or the side view over on this side. I would notice that it's completely hollow. Okay, and then inside, the inside circle here, let me use a different color here, looks like this. There's an inside circle that's ever changing. I should have drew that back line dashed or dotted. Okay, so you can see that there's this inside orange shape, this inside orange cylinder that's ever changing. The smallest one has a radius of 1 on that inside little circle in orange, and the biggest one would be the exact same one as this blue one, so the orange one varies. Thus the need for integration. Since we have a varying radius, we need to integrate infinite circles to really build this area up, and then thus to build the volume. Remember, we're stacking areas. We're stacking areas. In this case, we're going to stack the areas this way. I'm going to stack all these different areas, infinite areas. The integration then, if you look at it, will be, and again I want to illustrate this, a thickness area that is a delta x thickness. So each one of these areas that I'm stacking up symmetrically over here as well, okay, is a dx. Shortcut thinking is you rotate it around x, it is dx if you're using disk and washer. But there's the visual of why. If I'm stacking infinite disks, then I'm going to have an integration that is dx. And I think that's very important to understand, not just accept the little rule. All right, now the cross section. If you remember your geometry, there were several problems where we took a look at I'm going to try to draw a quick cross section. If I split this down the middle, let's say, and I looked at it like slicing open an apple and looking at the inside, I would see the cylindrical blue edge. The blue edge, it's the same edge all the way through. But on the inside, I would see then, in a sense, the orange radius circle. This is our little r. This is also why it's hollow. This on the outside is our big R. So what we have then is we have this continual area, that looks like this is cross section. Let me get a little better color there. So if I fill this in, we have this continual area where we're getting a pi r squared, remember your geometry, a pi big R squared minus a pi little r squared, a pi little r squared. That'll give us this area on the outside over here on the outside, okay, or the washer, as we like to say. Washer is a mechanical term. You could also use a ring, a thick ring. A lot of books use washer. I've seen books use ring as well. So what we have then is we're going to stack an infinite set of these rings. The smallest ring has a radius of 1 on the inside, and always has the same big R on the outside. The biggest ring has 0 radius. The biggest, or excuse me, I should say the biggest ring or the biggest washer is down over here, and the smallest one has an area of 0 at the x value of 2. And that's really important to recognize, that at the x value of 2, this is 2 comma 5. 2 comma 5 points. So at the x value of 2, then we will see, then we should have an area of 0 there. And we will double check that as we build this. So I've been very explicit about how come this formula works. I don't want you to just dive into it. So I'm basically taking an area of a pi, I'm integrating a bunch of washers of a pi r squared minus a pi little r squared, and then integrating that, in this case, from a to b generally, but in this case dxy's 0 to 2. Most of the time you'll see the formula with the pi pulled out, and that's appropriate, the typical integration rules. Let's go ahead and fill in our radius now. Big R, big R. Big R is the same. It is 5 every time. It's 5 everywhere. If I go down here, the big R radius is 5. So the big R radius is the y coordinate. I always have my students start off by identifying, are you moving vertically for this radius? Are you moving vertically for this radius? Or are you moving horizontally like we did with the disk? Once you realize that it is y, and we need it in x terms, it's y equal 5. So the big R is 5. So we have 5 squared. Little r now is ever changing. Little r is ever changing based on the parabola here in red, the x squared plus 1. So little r, if I drew little r, try to draw an example of it right there. So little r is, let me draw that in red so we can see it. Little r is, kind of like we did here, is a y coordinate, but it's based on x squared plus 1. It's based on x squared plus 1. I want to be sure you can see that. So it's based on x squared plus 1. Okay, now we can put that in. We are taking this radius squared, which is x squared plus 1, quantity squared, and this is still in terms of dx integration. So this is how we build a problem like this. Okay, so if we build this washer-looking, ring-looking object with a continual changing inside, more kind of like a funnel on the inside, almost a reverse funnel on the inside. All right, let's go ahead and do the math now. Pi on the outside. Let's clean this up before we integrate. 0, 2, that's a 25. Be careful of what I call the poster mistake, as I have a poster inside saying this is not the square of each term, that there's a middle term if you think of foiling. And also be careful of negative distribution. There are two huge common mistakes here. You might think you just square these guys. Be careful, it's much more than that. It is the square of the front, but there's a middle term of doubling the 2 multiplied. So that's a 2x squared and then the square of 1. Now we can go ahead and think distributing the negative as well as integrating. I think we can do both those in the same shot. So we still have the pi on the outside. We now have a 25x. We also have a minus. Distribute the negative here carefully. Do not make this mistake. A lot of students, including myself, will make this mistake at times. So be careful. So we have a minus. Add 1, flip and multiply. 1/5 x to the 5th, a minus, add 1, flip and multiply. That's a 2/3 x cubed, and a minus x, all between 0 and 2, all between 0 and 2. Pi, plug and chug at 2, plug and chug at 2. So we got 50 minus a, that's 2 to the 5th, that's 32 fifths, 32 fifths, minus a 8, 2 cubed times 2, 16 thirds, minus a 2, and then we would then subtract the plug and chug of 0, but if you look, every term has an x in it, so we'll be subtracting off 0. A little bit of calculation work to do, a little bit of calculation work to do. Please don't be afraid of this. Do not grab your calculator. Keep that part of your brain fresh. Even if your teacher allows you to use your calculator here, shame on them. Okay, you should be able to handle this and be able to play around with this and get this into at least something you can recognize and work with easily. The 50 minus 2 is not that bad. We have a pi on the outside. We've got a 48. Over here, we've got 2 negatives. Let's get them common denominators. So let's think multiply by 3 over 3, right? Multiply by 3 over 3 and multiply by 5 over 5. I hope you have the skills to be able to do this by hand. So this is 3 times 32. I broke that up on purpose. That's 96. So that's minus 96 fifteenths. And then you have a minus, that's 5 times 10, 6. I said that in more of a broken up style, so you understand how I do that. That's 50 and 30, that's 80 fifteenths, 80 fifteenths. Okay, you're going to be subtracting them, so we have a common then answer of pi 48 minus, what's that, 176 fifteenths. Again, don't grab the calculator. See, challenge yourself. Do this by hand. Do this by hand. I'm serious. Okay, so I know you might make a mistake, but you can check it with the calculator later and really always test your answers. Okay, or excuse me, test your calculation skills. 15 goes into 176. Let's see, little long division. Don't be afraid of it. 1 time leaves a 2 and a 6, right? So that's going to go in another 1 time. So that's then a remainder of what's 26 minus 15. You should be, I think you can handle that. Might want to show the work. Whoops, not there. 176. So that'll go in 1, 15, 26. That'll go in 1. I was right. I do want to subtract off of 15. So then I have 11. So I have 11. I'm subtracting off 11 and 11 fifteenths. So 48 minus the 11. 48 minus the 11 is 37. And then 37 minus an 11 fifteenths will take me to 36 and 4 fifteenths, just subtracting off the little combination of the 11 and 4 making 15. All right, let's rewrite this. I get 36 and 4 fifteenths pi. Okay, I technically should be grabbing a calculator here and double checking it. I leave that to you and make sure that I am correct. I'm David from Electric Teaching. I'm going to do some more volumes using the shell method in some later videos. I hope that I have helped.